Okay, let's do the questions on page 654, numbers 1 to 3. So number 1 says a carbon isotope, which is carbon 13. So it's 13.6. Its nucleus has a mass of 13.00335 atomic mass units. So that's the mass of our nucleus. And it wants to know what's the mass defect and the binding energy. So your textbook uses, like we did the other day, uses the mass of a proton to be 1.007825 U's and the mass of a neutron to be 1.008665 U's. Okay? And so we're looking for in part A, the mass defect, the delta M. And we know that's equal to the mass of the nucleus minus the sum of the masses of the neutrons plus the sum of the masses of the protons. So our mass defect is going to be 13.00335 U minus, so in carbon 13 there are 7 neutrons, so 1.008665, you're going to multiply that by 7, plus, and there are 6 protons, so 6 times 1.007825. Okay, so the change in M. First term, I'm just going to write out the two terms in case you screw the second one up. Second one should be 13.107605. And so when you subtract these, you get a negative 0.104255 U's, where of course the negative means it is being lost. Okay, so when those protons and neutrons go together, the mass gets lost. And then part B wants the binding energy. And we know the binding energy is just equal to the delta M times, oops, I was wrong, 931.48 mega electron volts per U. So the binding energy is going to be equal to this 0.104255 U's times the 931.48 mega electron volts times U. And I usually drop my negative here because I know it means it's being lost, right? And so when you do this, you get 97.11 mega electron volts. And so that lost mass is turned into energy that's holding the nucleus together. All right, number 2 is a very similar question, except this time you're using nitrogen 14. And the nucleus of nitrogen is 14.00307 U's, and part A wants the mass defect. So again, the mass defect is equal to the mass of the nucleus minus the sum of the masses of all the neutrons plus the sum of the masses of all the protons. So the mass defect is equal to that 14.00307 U's minus brackets. In this case, there's 7 protons and 7 neutrons, so 7 times 1.008665 plus 7 times 1.007825. So close the other bracket. So delta M should equal 14.00307 U's. The bracket should give you 14.11543, I believe, if I can see my answer correctly there. And you get negative 0.11236 U's. And again, the negative means lost. Okay, that's part A. And again in part B, it wants to know the binding energy. So again, you take this 0.11236 U's and you're going to multiply it by the 931.48 mega electron volts per U. And when you do that, you get a binding energy of 104.661 mega electron volts. Now in this one, there's a part C that asks, what's the binding energy per nucleon? And remember, nucleons are the number of protons and neutrons in the nucleus. So the binding energy per nucleon will just be the binding energy divided by the atomic number. In other words, 104.661 mega electron volts, and in this case 14. And you get a binding energy per nucleon to equal 7.4758 mega electron volts per nucleon. Okay, that is number 2. Number 3 is again similar. It's asking, or it's telling us that this time you have nitrogen again, but this time it's nitrogen 12. And instead of going through steps, it just goes directly to what's the binding energy, but you still have to do the steps. So delta M is equal to the mass of the nucleus minus the mass of the sum of the neutrons plus the mass of the sum of the protons. So delta M is equal to, whoops, I didn't write it down, but they did give it to us in the question, 12.011188 U's minus, there are 5 neutrons this time, so 5 times 1.008665 plus, and there are 7 protons, 1.007825, and so 12.0188 U's minus 12.0981 U. And you get a delta mass defect of negative 0.0798 U's, where again the negative means lost. Okay, so now we go to binding energy, and so it's going to be equal to that 0.0798 U's times 931.48 mega electron volts per U. And you should get a binding energy of 73.866 mega electron volts. And so then finally, binding energy per nucleon. So you're going to take that 73.866 mega electron volts, and per nucleon is 12. And so your binding energy per nucleon is equal to 6.155, I think there's another 5 there, mega electron volts per U. So if you were to compare this to the question on top, the one on top needed more binding energy, right? 7.4 per nucleon, down here 6.155. Makes sense because you have more neutrons inside the nucleus, more nucleons, and so you're probably going to need more energy per nucleon to hold them together, because to overcome the repelling forces. All right, and the last one is number 6, and it's kind of working backwards. In number 6, it tells us the binding energy. Okay, so it says the binding energy is 28.3 mega electron volts, and it tells us it's a helium, and it wants to know what must be the nucleus, the mass of the nucleus. Okay, so we know, first thing we can do is change to delta M, because we know binding energy is equal to delta M times the 931.48 mega electron volts per U. So that means that delta M is equal to the binding energy divided by 931.48 mega electron volts per U. And so 28.3 mega electron volts divided by 931.48. And so you get a delta M, wow, the lighting is awful here, I'm sorry, of 0, there we go, that's better. It's just the sun coming in the window on me again. Oh, and it's going to run out of time anyway. So you get here 0.